Hi everyone, today we're going to go over a couple of different additional concepts. So first, let's just go over k-means clustering, the steps for k-means clustering. So we need to provide a k value, the number of clusters. First step is we randomly initialize the different centroids. So we have a random initialization process where we're initializing the number of centroids. The number of centroids is equal to the number of clusters that we provide. Second step is to assign each data point to the closest centroid, and that will be their cluster for this first iteration. So assign each data point to the closest centroid, and we can do this through Euclidean distance. There's also other types of distances, but typically that's what's commonly used as Euclidean distance. So assign each data point to its closest cluster. And then now we have sort of our first initial groupings or first initial clusters. Then we recalculate the centroids. So the centroids are the average of the x's and the average of the y's. Recalculate the centroids, which will be the average of the x's and the average of the y's in each cluster. And then we reassign each data point because the distances are going to change. We reassign each data point based on the if what which centroid that they're closest to, right? Which cluster centroid that they're closest to, and then we iteratively repeat this process until we get to a point where in consecutive iterations of this algorithm, the clusterings don't change. So until convergence, when we get to a point where we have gone through this algorithm two times, have gone through these iterations twice, and the clusterings do not change. The clusterings do not change. That's when we know that k-means has terminated and we have finished running the algorithm. Couple things to know about here is we do require the number of clusters. So that's a drawback is that if you're given a data set and you don't really know how many clusters you even want in the first place, you just want a clustering, k-means that's one of the drawbacks. You need to specify the number of clusters that you want. So that's one sort of con. Another thing is because of this random initialization process, it's possible that you might get different clusterings each time you run this algorithm because the centroids will be placed, could possibly be placed at different points, and that may lead to different initial clusterings, and that may change ultimately depending on how your data is. But there's some cases that may change your overall clustering. So that's one of the drawbacks. When we see hierarchical clustering or other types of clustering, that's possible. It's possible that even during consecutive like runs of the algorithm, you get the same clustering. So for hierarchical clustering, that's the case because it provides nested clusters. If you run that same algorithm like twice, you will still get the same clustering. So that's one of the benefits of hierarchical clustering. These some of these other clustering algorithms is the stability of the results. So hierarchical clustering. So that's hierarchical clustering. Now let's just go over quickly hierarchical clustering. So what it does is it first treats every individual point. So if we're looking at bottom up, right? If it first treats every individual point as its own cluster, as its own cluster. Then it calculates the dissimilarity between each of these clusters, calculates the dissimilarity. Then we have our dissimilarity matrix here where we have our merged like data points. We have our points here, and we calculate the distance between each of these. Okay, so this is going to be a matrix, and then we merge the two most dissimilar clusters. The two most dissimilar clusters, we merge them, and then depending on the type of linkage that we have, so let's say this is A, let's say this is B, C, let's say this is D, A, B, C, D. We see that B and C were the most dissimilar. We've merged them. Now we have A, B, C as one cluster, and then C. Then we repeat the same process again. We figure out our distance matrix. If it's complete linkage, that means this dissimilarity is going to be calculated by using the max distance. So the maximum length, the farthest points in each cluster. So if we have a grouping here, and if we have another grouping here, if we have complete linkage, we're going to use the furthest point here, we're going to use the furthest point here, and this distance that represents the dissimilarity between these two clusters. If we're using single linkage, we're going to be looking at the points with the smallest distance. So we're going to be looking at this point and this point. We're going to see what's the distance here, and that's going to be your dissimilarity. So depending on the type of linkage, your dissimilarity matrix will be different. Typically, complete linkage and single linkage are used, and we have different depending on the clusters that you want, depending on the types of clusters that you want to identify. That depends on that will affect which linkage option you use. And now let's go over PCA. So PCA is a dimensionality reduction technique. It's also used for visualization. It's used to produce uncorrelated independent features. So this is also could be used in PC regression. If you have many correlated variables and you want to decorrelate them, make them independent in Fourier model, you can use principal component analysis. To do that, how it works is you take the covariance matrix, you get the eigenvectors and the eigenvalues of the covariance matrix. The eigenvectors become the loadings of your principal components, which contain the weights for each of the variables. So PC1 it has weight 1 times variable 1 plus weight 2 times variable 2, assigns a weight to each of the variables in order to get that principal component. They are orthogonal to one another, or they're also independent. So that's principal component analysis. We'll go over also a couple of different severity, frequency, and aggregate models. So survival function is the probability that x is greater than x, which is 1 minus our CDF. Now, this is also, so that's what we call survival function. Now let's go to hazard function. Hazard function, you can think of it as what's the probability that x is going to be that specific value, given that it's at least that value. So you can think of this as probability that x is x, given that x is at least greater than x. Right? This is typically the case for, if this is continuous. And let's see, so that's that. Another way you can write this is negative derivative of natural log of s of x, or of the survival function. Another way you can write this is the cumulative hazard function is equal to the negative natural log of s of x, and then survival function equals e to the negative cumulative hazard function. So these are the relationships that it's critical for you to know. Then we have, how do we find the mode? So the mode is the most frequently occurring data point in your distribution. So how do we find that? If we have a functional form of the distribution, we can take the derivative of it, set it equal to 0. That's going to provide our local and global min, global max, or local min or local max. And when we set this equal to 0, solve for x, x becomes our mode, the data element that's constantly appearing the most, that's most frequent out of the entire frequency distribution. Now we have variance of ax plus by. So this is so variance of ax is a squared variance of x. Variance of by is b squared variance of y. Plus we have 2ab times covariance of x and y. And now here, let's see, what else could we do? We have gamma. So another thing to note is gamma of n is equal to n minus 1 factorial. And we have coefficient of variation, so that's standard deviation over mu. Positive skewness, you can think of that as right skew. So positive skewness is right, being right skewed. And you can think of this is right skewed because the tail is on the right. So if the tail is on the right, that means it's right skewed. And likewise for left. And then we know about Bayes' theorem. We know about if probability of A and B equals probability of A times probability of B, if and only if they're two, A and B are independent. If they're independent, we know that the covariance of A and B equals 0. Empirical distribution. So what empirical distributions are is if we have 5 data points. So empirical distributions are if we have 5 different data points, each of those are assigned a probability of 1 over n. If we have n, in this case, 1 over 5th each data point. That's going to be the probability distribution. Now, the CDF of this So let's say we have the CDF of x, that's going to equal the number of observations that are less than or equal to x, the number of observations less than or equal to x over n. And if we're looking for the percentile, like if the question's like, what's the 75th percentile of this empirical distribution, what you could do is you could take n, you could take the pth percentile, so in decimal form, and you could just take the floor, you could take the ceiling of that. You could take the ceiling of that, and that's going to be, and that will be your k, and then the kth statistic on it, or the kth smallest observation, will be that percentile. So just as an example, let's say we have 2, 3, 4, right? Each of this probability is 1/3, 1/3, 1/3. Let's say we want to see what's the CDF of 3, or what's the, I guess, the 80th percentile. What we would do here is we would do 3 times 0.8, right? The 80th percentile. We get this to be around 2.4. We would take the ceiling of that. Ceiling of that is 3. And so we get that the 80th percentile is the third smallest value. So third smallest value is 1, 2, 3. Okay, so it would equal 4. And then let's talk about a bit about transformation. So if we have the CDF of x, what we could do is we could restate the CDF of x in terms of y. In terms of y. And what this allows us to do, and what I'm talking about is if the CDF of x is this, right? If we put this in terms of y, so if we know that this is the CDF of y that we're looking for, we're trying to find this, right? What we can do is we could replace y with x. And then we can use the CDF for x to solve. We know that, let's see, transformations, we know for Pareto distributions as well as for simple Pareto distributions, we do have that shift. So for both Pareto, so if it's Pareto and we have y equals, so if we have some x, that's a Pareto distribution, x minus d, given that x is greater than d, is going to follow, if we have a Pareto distribution, so let's see, of alpha theta, then x minus d, given x is greater than d, is going to equal alpha theta plus d. So it's that shift we see. Same thing with simple Pareto. So in simple Pareto or single Pareto, we have only one true parameter. So that true parameter is actually just alpha. The theta is the shift. So this is a shift of theta from alpha theta, right? And then if we do apply the same sort of transformation here, x minus d, x given greater than d, is going to equal Pareto alpha d. Pareto alpha d, because that's the shift. Okay. If we are ever asked to find the CDF of gamma, that's going to equal the gamma of alpha x over theta. Right? So see, this is f of x. If it's over gamma, this is what it's going to be. And this is a very messy integral, so we're not going to solve this, but what this is it's 1 minus the probability that n is less than alpha, where n follows a Poisson distribution of x with mean x. So once you actually solve that, you'll be able to solve that without having to go through the entire algebra of the problem. Okay, now the sum of many independent gammas are the gamma with the sum of its alphas, comma theta. Exponential distribution is the gamma with alpha equal 1. Exponential also follows the memory list property. So the memory list property states that whatever has occurred in the past does not influence the future. And we know that from the memory list property for exponential, it gives us this nice property that, hey, if x, the expected value, or the distribution of x minus d given x is greater than d is the same as the distribution of just x, so, which is just expo of some theta. And then, so in this case, the expected value would be the same, everything variance would be the same, everything would be the same here. Okay. Linear exponential families are Poisson binomial, gamma normal, and negative binomial, and these make up the generalized linear models. You're able to use that framework if the distribution falls within the linear exponential families. Now, scale distributions are such that if you multiply this random variable by some constant factor, it will increase the scale parameter by that factor as well, which is typically theta, while keeping all of the other parameters constant. So all the tables except inverse Gaussian that are in the exam tables are known as scale distributions. And then you also need to know law of total variances and law of expectation. So the law of expectation says that the expected value of x is equal to the expected value of the expected value of x given y. And the variance of y is equal to the expected value of the variance of y given x plus the variance of the expected value of y given x. Okay. I think that's pretty much it for now. I guess one more thing want to quickly go over. So this is what we call the Bernoulli principle. So if we have, and you can try to map a lot of these different questions that you're working on to this Bernoulli principle. So you have X, you have two outcomes, right? A or B. Probability of A is Q, probability of B is 1 minus Q. What's the variance of X? The variance of X is going to be equal to A minus B squared, Q times 1 minus Q. And then if we calculate the expected value of x, this is the upper limit or the policy limit. So anything from 0 to the policy limit, that's going to be x of f of x dx. So this is the expected value that the insurer is going to pay, plus anything from u, the policy limit, to infinity, that's just going to be the dx. So this is actually just this plus mu s of x. Okay. Mu times s of mu. And so there's typically a formula that you can look at in the exam tables for this. This is also equal to 0 to mu of s of x. Okay, I think that's it for now. Thank you for watching. I'll see you in the next video.